looking at Chapter 2, Section 2.3. In this lesson, we will look at solving contextual problems involving permutations of distinguishable objects. Recall that factorial notation, 5 times 4 times 3 times 2 times 1 can be represented by 5 factorial, and 5 factorial is a concise representation of the product of consecutive descending natural numbers. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5040. You could also evaluate factorials using the factorial button on your calculator. Let's look at an example. How many different possibilities are there when arranging the letters of the word music? Since there are 5 letters, and we cannot repeat each letter, there are 5 options for the first position, 4 options for the second, 3 options for the third, 2 options for the fourth, and 1 option for the last. 5 factorial, which is equal to 120 different options, or possibilities. How many different possibilities are there if the first letter must be an M or a U? If an M or a U must go in the first position, then there are only 2 options to go here. Once one letter is used here, then there are 4 left for this position, 3, 2, and 1, which leaves us with 48 possibilities. How many different ways can you arrange the letters in the word factor if the first letter must be in a consonant, that is an F, C, T, or an R, and the last letter must be a vowel, an A or an O? If the first letter must be a consonant, there is 4 options for this first position. There are 2 options for the last position if they are to use a vowel. That will give 2 out of the 6 numbers already used, leaving 4 for the second position, 3, 2, and 1. Giving us 192 different possibilities. A permutation is arrangement of objects in a definite order, so order matters. For example, how many ways can John, Bill, and Fred be seated in a row? So we can have John, Bill, and then Fred, and of course John can remain in the same seat, yet Fred and Bill would switch. These are different arrangements. Even though the same people are involved, they are sitting in a different order. We could put Bill in the front, then John, then Fred. Bill remains in the same seat, but yet Fred and John could change. Once again, all different arrangements. Fred can then go in the front, Bill in the middle, and then John. Fred, John, and then Bill. We see that there are 6 different ways. It is a permutation of 3 elements taken 3 at a time. Permutations can be given by the formula n permute r, which equals n factorial over n subtract r factorial, and r is greater than or equal to 0, but less than or equal to n. This formula will also be given to you on the formula sheet for your exam. Let's have a look at an example. How many ways can 5 students be elected for president, vice president, and secretary? We see that is 5 objects at 3 at a time. There are 5 options for president, 4 options then for vice president because 1 is already president, and then 3 options for secretary. We say that it's 5 permute 3. We have 5 factorial over 5 subtract 3 factorial, which is 5 factorial over 2 factorial. And of course, these are common, which is going to leave us with 60 options. Let's have a look at another permutation. How many different ways can 4 students be selected for president, vice president, secretary, and treasurer? That is 4 objects taken 4 ways. That is 4 permute 4. We see that we get 4 factorial over 0 factorial, and recalling that 0 factorial is 1. That will give us 24 different ways that these students can be selected for president, vice president, secretary, and treasurer. Having a look at an example, a tennis club has 15 members. They are electing an executive committee of president, vice president, treasurer, and secretary. How many different committees are possible? So we have 15 objects taken 4 at a time, which is 15 permute 4. We see that it can be 15 factorial over 11 factorial, and 11 factorial can cancel out. This would give us 32,760 options. 32,760 committees that are possible. Permutations can have specific cases or conditions. For example, Riley and Chase are on a hockey team with 13 other players. That means there will be 15 players in total. How many different starting lineups of left wing, right wing, center, left defense, and right defense are possible if Riley and Chase must be center? And here's our condition. Riley and Chase must be center. So if Riley and Chase are center, that means we have 2 options for the 1 position. And we see that there's 2 ways that this can happen. For the 4 other positions, there are 13 people left that can play those positions. 13 can play each of the 4, which would give us 17,160 for those 4 positions. We need a center and the 4 other positions, and therefore we multiply the 2, and we get 34,320 different starting lineups. Keep in mind that if we use the same 5 people, yet in different positions, that is different starting lineups. If Riley is center and another person on the team is right wing, that is a different starting lineup than if Riley is center and that other person is left wing. That would be a different starting lineup. Let's have a look at an example. N permute 2. So we can substitute in for n, and 2 in for r. And we get a factorial equation. This is just another way of writing a factorial equation. So we rewrite n factorial as n times n minus 1 times n minus 2 factorial. We can then cross out common factors and move the 20 over so we can have one side of the equation equal to 0. We use factoring, and we see that n can equal 5 and n can equal negative 4. Yet when we substitute negative 4, we have negative 4 factorial, which we know is undefined. Therefore, we must reject this value. Let's have a look at another example. Once again, this m plus 1 will be n in the permutation formula, and 2 will be r. And we see we have n plus 1 factorial over m plus 1 subtract 2, which is n minus 1. In reducing, or rewriting rather, the n plus 1 factorial, we have n plus 1 times n minus 1 factorial. And once again, we cancel the common factors. That will leave us with n squared plus n, and we'll move the 72 on the other side of the equation so that one side will be equal to 0. We can factor to solve for n, or another option would be using the quadratic formula. And we see that n equals 8 and n equals negative 9. Yet once again, negative 9 is not possible, since negative 9 plus 1 factorial will give us negative 8 factorial, which is not defined. We will reject n equals negative 9. In summary, the number of permutations from a set of n different objects, where r of them are used in each arrangement, can be calculated using this formula. This formula will be given to you on the formula sheet. For example, if you have a set of 3 objects, A, B, and C, but you use only 2 of them at a time in each permutation, the number of permutations would be 3 permute 2, or 6 permutations.